one of the things I noticed when I was going over the last week's worth of stuff is these are these 4 pages of notes or whatever they are, 2 pages both sides, are the things that I've picked up, giving you these packets that you're basically going to need to review, because they're from Chem 1, a lot of these concepts, and some of them it's just a terminology thing. All right, like for example, yesterday they asked about the Bohr model of the atom, and you say, well, I've never heard of that. I have no idea what they're talking about. What's the and you're right, I never use that term. Okay, because basically we're talking about quantum theory, and we talked about a lot of the stuff in the quantum theory, but I never really mentioned the Bohr model, because as you can see from, again, you don't have to write any of these notes down, they're kind of already there. It was an earlier atomic structure model, all right, that was pretty accurately predicted things, all right, but has been superseded by the quantum model, all right. And what does it all say? What do both basically say? Well, the Bohr model was basically saying things that we already know. Electrons can only exist at certain energy levels. He realized that. There was like no way it could just exist anywhere. It had to have little specific quanta of energy. All right, because you were getting, well, there's a lot of reasons, but you were getting, you get specific wavelengths of light that are given off when these electrons change energy levels. So he predicted these circular orbits for electrons going around the nucleus, and specific distinct energy levels. Now, his model falls apart once you get to larger atoms, and it doesn't take into account some of the things that we now believe about the modern quantum theory. For example, the orbits are not circular. Okay, we don't have circular orbits. We have different shapes of probabilities. The uncertainty principle and probability, we like electron cloud of probability that I can have in a particular shape. It's spherical for an S-shaped orbital. All right, but it can be P-shaped, T-shaped, and you've seen all of those before. So those things are incorrect. And something else about his model, like if it were true, he had no way of understanding or explaining why that electrons, given this model, should be falling into the nucleus. They should lose energy, lose momentum, and fall into the nucleus. Of course, that doesn't happen either. So we've improved on the Bohr model, but it was actually used, okay, the same basic theories about distinct energy levels and changing are still used today to do very simple calculations. Again, it doesn't work for every atom, for larger atoms, but it works for hydrogen in particular. And so there are questions about the Bohr model, and especially in regard to hydrogen. We understand it pretty well. And what you'll see, basically what he's saying is happening here, is that electrons are excited from, say, first energy level up to the fourth. They drop down oftentimes in stages, and there are different places they can go to and from. And this actually been mapped out very well by, for the hydrogen atom. It turns out the electrons can exist in multiple different states, and they can make different changes. And each one of those changes corresponds to a specific wavelength of light that's given off, a color, all right, that we can see. And we see that, all right, oops, I went too far. We see that. Remember these? Remember doing these? This is all part of the question they were asking you on that last test. We did do these. I gave you spectroscopes. And I said, here are some spectrum tubes where we excite electrons. Hydrogen was probably one of them. Helium was definitely one of them. Mercury. Neon. Remember neon? Put neon in there. We looked at them through there, and we saw these bright lines. You guys looked through them yourselves, and you drew them, I think, even. And you did calculations for delta E equals hc over lambda, and C equals frequency times wavelength. All of that stuff we did do in Chem 1, but we haven't really talked about it. The Bohr model is saying that line corresponds to a specific change by an electron from energy level, say, 2 to 1, or from 4 to 2, or whatever they are. And if you actually were to draw them out, these are the different changes that hydrogen electrons can make. There's what's called the Balmer Series, which is in the visible spectrum. There's a red line you'll see, a green line, a blue, and a violet line that you can actually see for hydrogen. There's other electron changes that can be made with hydrogen, but you can't see these because they fall in the UV range, and you can't see these because they fall in the IR, the infrared radiation range, versus the ultraviolet radiation. But the ones that fall, and all these pictures, by the way, are on your papers there, in the visible range, you can actually basically tell what the electrons are doing. Right? They all correspond to specific changes by electrons, specific energy level changes by electrons, when they fall back to their ground state. Now, I did talk about that. We did flame tests on that. Remember the flame test? Flames burned, let me get to that one here. We would burn a flame. Strontium, for example, burns red. We'll put a little bit of barium chloride into a flame, and it burned like a yellowish green. If you were to look with the spectroscopes at those guys, you would see something that would look like these. These are the atomic spectrum. Okay, these are generally the emission spectrum versus the absorption spectrum, which would look like this, where these are the things that are not being the holes that are there, basically. That's for the sun, anyway. But these are as different as fingerprints. They're used to identify atoms. They're used to identify them based on this. And these wavelengths correspond to specific electron energy changes falling back to their ground state after they're excited. Now, all of that is stuff we had in Chem 1. But did I call that, the way they were talking about it in the last test you just took, you probably had no idea that's what they were talking about when they mentioned the Bohr model of the atom, right? And a lot of that's terminology, all right? I never use that word. They use it, and they don't say a whole lot about it, and all of a sudden you're completely confused. You have no idea that's what they were talking about. But you did see it. There are very few things on here. As I'm doing a test now that you're going to take next week, I'm doing it myself without even looking at the key, seeing, I'm getting more and more frustrated as I do these because I'm realizing how they're deliberately asking questions to confuse you. And they ask really bad questions. I mean, if I were on I hope somebody's watching this, someone who makes up these test questions at the AP exam. There's no good reason, idiots. I'm not talking to you, I'm talking to the idiots who make these tests up. To have, the next 5 questions are based on this scenario of multiple choice questions. 5 questions are going to be based on the scenario. And then they're going to make that scenario so confusing that you make one small little problem. You're going to see this in today's thing I'm going to give to you. I'm going to try to clear that up in the next few seconds. One mistake early on, and that mistake will carry through to each of the next 2 or 3 questions on it. No good teacher does that. No good teacher makes your prior mistake be carried over to the next 3 questions you're going to be asked. And that's what they're doing in a lot of cases. So you got to be very careful that you're interpreting what they're giving you in that scenario, whatever that scenario is for those next 4 multiple choice questions, that you're interpreting that correctly, or it will cost you for everyone. I noticed that. You're going to see it today. People got the first 4 questions of this next test either all right or all wrong for that reason. And that's just stupid. And there's no reason to do that. It's not testing someone's knowledge of a topic by setting you up for failure if you make one dumb mistake and then carry that dumb mistake on, even though you're doing everything else right after that. But I'm just saying, it's going to be very frustrating for me as I'm watching more and more of these and taking more and more of these and giving more and more of these to you guys. I'm realizing how this is, I hope to God the actual AP exams, not these practice ones that we're taking, aren't this bad. But my guess is they probably are. They're deliberately putting every question, every answer that you would make the dumbest little mistake on, they're putting it down there so that you'll make it. Anyway, so that kind of covers what I wanted to talk to you about, the Bohr model of the atom and basically spectroscopy and all that stuff. Now, I want to spend a little bit more time today, because the one you're going to be taking today is going to be all about periodic trends. Now, I realize, although in a previous review thing, I talked about how you could always tell, in general, what's happening, and hopefully you know this. But now I'm going to ask you it's going to ask you on this test, and you could certainly be asked on the AP exam to explain it. And I want to explain why the highest electronegativities and the highest ionization energies are generally up here, and why your best metals who lose electrons in your largest atoms are down here. Pay attention to this. If you do, I am about to answer over the rest of this many questions coming up. Okay, you don't need to copy this. This is already in a previous packet. This is it's the same things in the packet, but I want to explain it to you today. All right, let's take a look. We all know as I go down a group, the atomic size gets bigger, right? As I go down a group, atomic size gets bigger. Why? It's not what you think. Well, I just asked this. I know this question is going to be asked to you anyway. You'd say a couple of good answers you would think are good answers. Well, here's hydrogen way up here, and here's rubidium way down here, or francium way down here. He weighs more. He's heavier. He's got more protons, and he's got more electrons. All of which are bad answers. None of those are correct. As I go down a group, it's not because I have more electrons and more protons. It's not because he weighs more. And my favorite bad answer, when I've asked this on my test in Chem 1, you may remember this, I would ask a question like, explain why atomic size why atomic radius increases as you go down a group. And people would say, atomic radius increases as you go down a group because the atom gets bigger. What's wrong with that answer? It's restating the obvious, right? Why does it get bigger? Anybody know?
Yeah.
Why?
Because it fills up more energy levels.
Exactly. If I'm way up here, I only have one energy level. That is the big reason. By the way, we're gonna build on this each time. I'm gonna ask you different questions and kind of build on this. Here's hydrogen. He has one proton. He has one electron. He's got one energy level filled. But because of the quantum model of the atom being in energy levels, and the definition of an energy level is the average distance of the electron from the nucleus in terms of probability, the average distance from the nucleus. Okay? As I go down, I'm adding a second energy level, a third energy level. When I get down to the bottom, I got 7 energy levels. Okay? So all of those energy levels, okay, by definition, have to be further from the nucleus because an energy level is, by definition, the average distance from the nucleus. Okay, so there I got my electron here, great. Now, notice why I didn't accept, I'm going to explain now why I wouldn't have accepted just because it has more protons and electrons. As I go across, what happens to the size of the atom? It gets smaller. The guy over here is about half the size as the guy over there. Why? On a given period. No. If I'm going across a period, am I adding any energy levels or am I going down any energy levels? No, I'm just filling up the energy level I have. Okay? Why would you expect, as I go across, these guys actually get smaller? What do you think?
Because there's more electrons around the nucleus.
And?
More attracted to the positive side.
Well, yeah, actually, it's more of the fact that there's more protons in the nucleus, and there are more electrons as well. So basically, and this is another question you're going to get if you didn't already see it, something called Coulomb's law. All right, now, I never told you, again, another terminology thing. I never used the word Coulomb's law. I never said that. The Coulomb's law basically says two things, and there's actually a formula for it, but you're never going to be asked to calculate it. Even the book said it's unlikely that you'd be asked a question calculating something about Coulomb's law. But here's what it basically says in the equation. The greater the positive charge and negative charge, the greater the attraction. The more plus charges I have, the more protons I have, and the more electrons I have, the greater the attraction. Wow, that's tough. And here's another one. The distance matters. The closer those electrons are to these electrons that are flying around out here, the closer they are to that one, if they're further out, they're not going to be held as tight if they're further out. Both of which I told you. All right? Both of which I told you when we were doing this in Chem 1. Neither of which did I call Coulomb's law. But that is Coulomb's law, basically, in a nutshell. The more positive and negative charges you have, the greater the attraction is going to be. The stronger the positive charge, the stronger the attraction. And the closer they are to there, the stronger the attraction. Okay, so as I go across, you're absolutely right. I'm getting more protons and more electrons. Stronger positive and negative charge is going to be, even I'm filling up the same energy level, is going to be kind of pulling that guy in to the middle. All right, now, let's see how that affects. I can use that one trend along with one other thing I'm going to get to in a minute. This one trend of atomic size, being able to explain that, will help me explain electronegativity, ionization energy, and metals very well. Let's see. As I go down, what would I expect is going to happen to the attraction of electrons, since up here, they're very close to a nucleus, and down here, they're very far away. It's going to decrease. So as I go down, it's no big surprise. It's no surprise that as they go down, the electrons are getting further from the nucleus. It's going to be easier to remove them. So what happens? Very low ionization energy. It doesn't take much energy to pull an electron away. That's what ionization energy means. The energy needed to make an ion. You make an ion when you pull an electron out of them. Lowest electronegativity. It's not attracting electrons very well down here. Right? Makes sense. But there's a second reason why. There's a second reason. Besides the fact that this electron's further away, what's in the way of the charge of that nucleus? All these other... You remember what that's called? The shielding effect. Exactly. Your book, I believe, the new one I got here, actually calls it something else. But shielding effect is what I've always called it. Okay? The shielding effect means that these inner energy electrons are going to block the outer electrons from the full pull of the nucleus. So for those two reasons, as you go down a group, electronegativity decreases, ionization energy decreases as well as you go down a group. It gets easier to remove an electron, less electronegativity. All right, and you're going to get your best metals down here. Your best metals are going to be down here because metals, by definition, want to do what? They want to lose electrons. All right, now up here, why? There's two reasons as I go across. Obviously, one of the reasons is atomic size decreasing. The protons and the electrons are going to be closer here than they were over here. Okay, they're closer together, so it's going to be held tighter, Coulomb's law. But there's another reason. What's the other reason why a guy over here is probably not going to want to lose electrons? Yeah, the octet rule, exactly. He wants to gain electrons. He's very close to having an octet. All right, so for both of those reasons, I hope you all would be able to explain these today when you get that test. And you're going to get that test. These same exact questions are coming. Okay. Now, one of their favorite things I like to do, I've noticed at least in these practice tests, is ask lots of questions about not just one ionization energy, what we call first ionization energy. Listen, but rather the second and third and fourth ionization energy. So I want to talk about that as well. Okay. Remember this kind of stuff? Okay, watch this. If I gave you, I'm just going to make up some numbers, but I want you to see what I mean. Okay? I'm pretty sure these numbers are relatively close, but I'm going to just make up some numbers. If it gives you, and it will in this test you're about to get, and by the way, you should have a page in the bottom of the page, I think, on the second side. If I gave you some numbers like this, what would you expect it's going to take to remove the first electron from a sodium atom? Do you think that would be a large amount of energy? No. He only has one electron in the entire energy level. All right? He's not paired. He's not filled. Nothing happy about him. And let's just make up a number. I think it's like 119. You can write them in. You can write these numbers in because these are fictional, but it doesn't really matter if these are real or not. All right? To remove the next electron, where has it got to come from? Yeah, not just that it's coming from a P, but that it's coming from an octet. If you look at it in the periodic table, sodium lost an electron, he drops down to a whole lower energy level. It's going to be really hard. It's going to be like 1,085, I think, is the number. But either way, it's like 10 times the increase. Okay? Let's go down to magnesium. Magnesium, to remove his first electron. Now, again, he's only got 2 in the whole outer shell. You say it's not going to be a large number, but will it be larger than this one? Yeah. Why?
Because he's paired.
Because he's paired, exactly. And he's a little further away, which means he's a little bit smaller. And so let's just think of a number like 138. Okay? It's going to be a little bit greater. To remove the next one, you might say, well, you've removed 1. To remove the next one might be easy. It's never easier. Remember Coulomb's law. I'm going to have a greater disparity now in the charge. Okay, he's not going to like that. He's not going to like that. So it's going to be like, maybe 312 or something like that. It'll be double or triple or whatever. 342. I don't remember the exact number. Here's the key. He's now lost these 2. What's going to happen when you go to remove the third electron? Big number, maybe like 18, whatever. So it'll be a huge increase. Okay? A huge increase. Now, lastly, and this is kind of a big deal because the test you're taking, I'm going to change something on it. Because as I went over the key, I didn't even notice until I had already given them out to period 1. The test is wrong. It's clearly wrong in the question it's asking. Because what happens here is, you might think to yourself, this guy's going to be a little bit higher than that guy, wouldn't you? You might think that. But he's not. Why not? He's not paired. The P shape isn't as stable. So maybe like 120 or something like that. It's going to be more than this 125. I'm just making up these numbers. But the point is, it's going to be more than sodium, but less than magnesium, which is unusual. Normally, as you go across, I would expect it to get harder. Remember that graph? I'm going to go back to that graph in a second that had the steps in it. Remember that? Remember that? Those steps occurred between magnesium and aluminum. Here's aluminum, here's magnesium. It actually drops for some crazy reason. We know the crazy reason. In general, it should increase, but it doesn't. All right, next number is going to be pretty high, maybe like 400. The next number would be higher than that, maybe 650. But where do you get the big jump of like maybe 2750? You get it after these first 3 are gone, and you got to break this octet. Okay? So again, this is just a review. The actual numbers are in your notes from Chem 1, but this is basically what you would expect to see. Okay? Now, before I go back to that other thing, I want you to just copy, while we're still talking about electron configurations, copy these two things down, because they showed up yesterday too. I had no idea they were going to ask questions on paramagnetism and diamagnetism. Copy those two things down. You have just enough room there. I just added that on there. It's actually not a difficult concept, and I'll explain it, but just copy it right now underneath where it says successive ionization.
Does the packet tell you like how to get the first electronegativity thing, or like just to get how to get that number? These numbers would be given to you, or they would just be talking about them. Yeah. Okay. So you don't really need the. You certainly aren't going to have to memorize numbers, obviously. All right, so copy those two things down. Let me explain what's going on there.
This is the arrow. Please call 3101. This is the arrow. Please call 3101.
So, if you were to look, this is from yesterday, if you were to draw out the configurations of those guys, you would find that one of them, only one of them, if it asked for a paramagnetic, had unpaired electrons. Okay? I don't know. It could have been. I don't remember which one it was. But let's take a look here. Basically, you don't have to worry about the inner stuff for the most part, do you? The inner stuff is always going to be paired, right? Because you know how that fills up. 1s2, and then 2s2, and then 2p. And they go in one at a time in a 2p. That's Hund's rule. Remember Hund's rule? And they come back and pair up. But if it's filled, they're filled. You're good. So we're just going to look at the outer shell. Right? The outer shell here. 3s1, how would that be drawn? It would be drawn with one electron. It's unpaired, therefore paramagnetic. Magnesium, however, would be drawn like this. An s fills up with two electrons like that. He would be diamagnetic and not attracted to a magnetic field. How about 3p1? It would look like that. And so would, and 3p2 would be like that. So he would also be, anytime you have unpaired electrons, you would have paramagnetism. Okay, so that's just the one little thing about that one that I wanted to point out to you. All right, now this also showed up in the last couple, not the last test, but the previous test. And this is one that Emily asked the question where I was very upset because I understand you don't remember how to do this, and I guess it's a good thing she asked that because I'm realizing how little of Chem 1 you do retain, and I kind of have to go over this before the exam. Empirical formulas. I would hope, what's the disappointing question about that is that you all understand that that's an empirical formula, that's an empirical formula, that's an empirical formula. An empirical formula is just the ratio of atom in a compound. Those are all empirical formulas. Molecular formulas, well, for example, C2H8 is not an empirical formula. Why not? It's not a simple whole number ratio. C6H12O6. Also, not an empirical formula. The empirical formula would be CH2O. All right, so that's the difference between them. All right, and we'll talk about that when I do my next example on the board. But let's just start off with, that's not the hard part. The hard part is, if it asks you in a question, can you calculate the empirical formula given information? You don't have to copy, this is all done for you. Given information like this. I give you there's a compound's made up of 39 grams of tin and 10 grams of oxygen. What must this formula be? Well, all you would have to do is this. Convert them both to moles, because we want the mole ratio, right? Convert this guy to moles, tin, atomic mass, 39 divided by grams of bottom, moles on top, you get 0.332 oxygens, and then you simply divide by the smaller of the two numbers. And you get 1 to 2. And that's why that's your answer, right? Your answer is, as I'll show you here in a second, after you divide them, your answer is SnO2. It's a 1 to 2 ratio, okay? Now, that's nice and easy, but it won't be that. You know the AP is not going to be that easy. Most likely, you'll get a problem like this, which I want to do together with you. So I hope you have a calculator out. I want to do this quickly. Okay, and watch. We have carbon, hydrogen, and oxygen we're going to do. And we're going to have to do, well, for carbon, 40.9%. First of all, don't let that percent screw you. All right, 40.9%, I can assume any sample size. Why not assume 100 grams? Because what's 40.9% of 100 grams? 40.9 grams. Convert that to moles. Grams at the bottom, moles at the top, 12.011. Do the math for that for me, Jared. And while he's doing that, let's set up H real quick. H is 4.58 grams. Grams at the bottom, moles at the top. 1 mole contains 1.0079. Do the math for that, Emily. And then oxygen, I've got 54.5 grams. Grams at the bottom, moles at the top. 1 mole contains 15.999. Do the math for that one there, Benjamin, Jacob, whatever, Ben Kinney. All right. First one, what'd you get?
3.41.
3.41 moles. Second one.
4.54.
4.54 moles. And last one.
3.41.
3.41 moles. So that is your ratio. It's just not in whole numbers. So we'll divide by the smallest number, and we will not, unfortunately, be done. What's the smallest of the three numbers? 3.41. So we'll divide by 3.41 in every case. And what I get is 1 to 1.33 to 1. Now that is your answer. Technically, it's just not in whole numbers. Your answer is C1, H, don't write this down, 1.33 to 1. What can I do to make them all whole numbers? I'm going to have to find the smallest number I can multiply this guy by so that I can round him up to be a whole number. And that would be a 3. Okay? And that's going to be 4. Then if I do that to him, I got to do it to everybody. And so your answer is C3, H4O3. But you're not done anyway. Look at that question again. I told you, this is much more likely the kind of question you would get in a free response question. Because it's obviously taking you a long time to do it. Right? You have a lot of stuff to do. I would hope they wouldn't ask something this difficult in a multiple choice one. But certainly you could see it as a free response. So, look up here. It tells me the molar mass is 176.13 grams. And I just found this to be the empirical formula. Anybody got a suggestion on what I could do?
Yeah.
What?
Find the grams for about that.
Yeah, we'll find the molar mass of this guy, and we'll see how it compares to that guy. Right? If you find the molar mass of that guy, it comes out to be like around 88, I think, or something like that. Around 88 grams, which is approximately half of this guy, right? And so what you do is, your final answer is C6H8O6. You multiply all those subscripts by 2. It's actually twice as big. Okay? So those are your empirical formula problems. Okay, almost done here. A couple more things to do. I should be on the last page now after this. I have a few things for you to write down there. So there you go. All right, everybody good with that? Let's go to the next one. Limiting reactant showed up a bunch of problems so far. You know what? Even in the one I'm doing for Monday, I'm doing that one on my own. I have not had time. There is no way I can do all the tests and do every single problem and every single one of those tests for you ahead of time in my first year teaching this, because I've given you, like, how many of these tests. However, I've been looking at, and we have more to come the whole next week. So I've been looking over, randomly sampling them and seeing what you guys are doing wrong. And generally, limiting reactants popping up all over the place. First, let's get the concept across. Concept is simple. The guy present in least amount, least abundance, is going to limit how much you can make, like in my example from Chem 1, right? If every hamburger, every cheeseburger has to have 2 tomatoes, 1 piece of cheese, 1 bun, and 1 hamburger, and I give you, that's going to my refrigerator, and that's what I've got there. How many total hamburgers can I actually make? Everybody agree it's 3. I can only make 3, and I'll have left over 3 pieces of cheese, 1 tomato, and 1 bun. Okay? All right? So that makes sense. All right? Now, the thing is, if I wanted to make it that way, all right, and I only had, this is the crazy part. I want to cross out some of these guys. If I had only 4 tomatoes, even though I've got more tomatoes than I have patties, who's the limiting reactant?
The tomatoes.
The tomatoes. So it's not always the exact whole amount of it. You have to take into account the coefficients, which I'm going to do right now. Okay? All right? Look at these examples. You already have, you're just going to fill in the answers here with you. Okay? You're already on there for you. All right, let's look at the first one up here. Okay? I gave you a hint. What was my hint? It's written on here. But what was my hint from yesterday I told you about? Yeah, just divide however many moles you have by the coefficient of that compound. And then the smaller number will be your limiting reactant. So in this case, it's going to be 1 divided by 1, and this will be 4 divided by 2. 1 divided by 1 is 1, 4 divided by 2 is 2. This is a smaller number. Magnesium is your limiting reactant, correct? So I would box him or circle him. And now, some of you are probably wondering, well, what does that tell me anyway? Why do I care? Here's what that tells me. It tells me I'm ignoring him. He is not going to determine how much magnesium chloride and hydrogen I get out of this guy. It's going to go from here to here. 1 mole of magnesium is going to give me 1.0 moles of that and 1.0 moles of that. You see?
Yep.
Okay. Now, let's look at this guy down here. I'm skipping this middle one for a second. I'm probably never going to do him anyway because we're going to run out of time. But look at this guy. I will talk about him. Let's skip down to this guy. Try the same thing here. 7 divided by 4, 6 divided by 3. Well, I know 6 divided by 3 is a 2, right? 7 divided by 4 is what? Yeah, it's 1 point something, right? 1.75.
Yeah.
Okay? So who's the smaller amount?
H3.
Right. So he's my limiting reactant, even though I had more of him. I had 7 moles of him. You got to be careful. Second thing to do on this problem, let's remember how to do these in our heads. Look here, quick. If I know I'm using him, I've got 7 moles of him, I'm going to here. What's that answer going to be? How many moles of nitrogen will I get from this guy? 3.5. And over here, it's ugly, but try it this way. Try it this way. If I know he's 3.5 and he's a 6, what is it going to be? 10.5.
Yeah.
Is it right? Because it'd be 2 times that is 7, and then another 3.5 is 10.5. Right? Okay? All right.
Oh, that's easy. Okay.
Yeah, now, last thing about, I said I wanted to talk about this one even though I don't have time to do it. Do not be fooled by grams. Grams tell you nothing if you don't take the moles of it first. So you would have to take your 24 grams and convert it to moles. Grams at the bottom, moles at the top. 1 mole contains 24 grams of magnesium. And watch how they did. Isn't that annoying? Isn't that annoying what they did there? They do this all the time in the multiple choice questions. All right? They will give you numbers. Then they'll say you can't use your calculator, and you can't, by the way. I'm sorry. And then if you're not thinking like this, and that's why I've tried to point this out to you a couple of times, you will have to round off on the periodic table. Not worry about significant figures. Just try to get approximate amounts. So 24 grams times grams at the bottom. Don't do this. Is 1 mole contains about 24 grams for magnesium, right? Is basically 1 mole, right? So I've got 1. This is the equivalent of 1.0 moles. 36 grams of HCl. Can you do an approximate amount for HCl in your head? 35.5 and they're 36. About 36, right? So 36 grams times grams at the bottom, moles at the top. 1 mole contains about 36 grams. And you start doing, when you do it like this, you start thinking to yourself, did I do that right? Is that, it seems like it's weird. He's actually put 1.0 moles. So I got 1 mole of magnesium and 1 mole of HCl. Who is my limiting reactant? You got to divide by the smaller number, or divide by the coefficient, and that gives you a 0.5 here, correct? Now, if HCl is my limiting reactant in this case, and he is, and I have 36 grams of him, I can't tell how many grams of this guy I have, but I can tell how many moles I have, right? 1.0 mole, I'm sorry, well, no, 2 to 1 would be 0.50 moles, right? And 0.50 moles, which I can then convert those to grams to get my answer. I know, it's a pain in the neck, but that's what you have to do. All right, last thing for you to copy at the bottom here before I close this up, because we're running out of time. These, I realized as I was going over these, are the prefixes that, granted, we should know 4 or 5 of those just from using them all the time. Kilo, centi, milli, we use them all the time. I've put the other ones on here because the other ones, you will see nano. Most likely. You're going to see nano somewhere. And you may see giga. It's not gija. It's not gidget. Giga. Now, those two, I would hope, are relatively familiar to you. What are they familiar to you from?
Gigabytes.
Yeah, exactly. Gigabytes and megabytes for your phone data and for your computer's RAM and hard drive. And for meth, exactly. All right. Kilos, that's kilos. That's weed. There you go. Dandelions, all those kind of weeds. All right, so, guys, I want you just something for your head, okay, to keep track of. I think most people probably could figure out deci versus deca being 10. Centium, milli we use all the time, so that shouldn't be a problem. You know, 1/100th, 1/1000. These next two, just look here. The next two go by factors of 1,000, right? So after you get smaller than milli, the next one's going to be micro, which is -6, and then nano, which is -9. And, oh, yeah, you could keep going. Pico would be next. Pico and the man. Now, I'll go in the opposite direction. It's mega and then giga. And you should remember that just in the fact that you should know. Gigabytes, yeah, next, I bet you exactly, the new hard drives now. I say new now. Somebody's watching this video, which no one will be 100 years from now because it's going to be like, you know, global warming will have flooded the earth and we'll all be dead. But if anyone were watching this 100 years from now, and they're all watching this saying how right I was that global warming didn't do that, they'll be saying, remember back when they had those little things called, you know, gigabytes? Like, because everybody was working in terabytes and beyond that, you know, gajillion bytes, whatever. But yeah, your newest hard drives nowadays, when you buy the hard drives, they're in terabytes for the most part.
They're going to subscribe to your channel?
Yeah, they're going to subscribe to my channel when they're all driving their hover cars, you know, and walking their...
Teleporting.
Walking their rocks.
Walking their rocks. Their pet rocks came back somehow. I have no idea. Pet rock. Remember those? And remember virtual pets? Did you guys ever have a virtual pet?
I had weapons.
Yeah, well, theirs are just going to be taller.
Yeah.
I had 54 weapons.
Anyway, is that the last page, I think? All right.
No, it's after Terra.